Okay, so let's recap the Bianchi identities that we saw last time. Okay, so we saw that there are two Bianchi identities, and these Bianchi identities are satisfied for a Riemann curvature tensor with defined on a metric connection, okay, without torsion. So this is a metric connection without torsion, and we saw that that Riemann identity, Riemann curvature tensor satisfied two identities, okay. Besides some other symmetry properties, it had these two constraints on it. These are called Bianchi identities. The first one is an algebraic constraint, okay, which means that it doesn't involve any derivatives. Okay, just some combination of the Riemann tensor components. You add them, you get zero. Okay, and the way to remember it, you keep this upper index fixed. Okay, and the lower indices, if you cyclically permute them, the sum of that is zero. Okay. Now the next thing is this the second Bianchi identity, which involves a derivative. Okay, it involves this affine connection. So its derivative with respect to kappa r c lambda mu nu. Okay, and here what you do is you cyclically permute the kappa mu nu. Okay, and you get the second term and this third term. Okay, and this sum is also zero. Okay, and I think as Toshif asked last time, right? Doesn't this the second Bianchi identity didn't seem to impose a constraint on the independent components of the Riemann tensor? That's because this is a derivative constraint, so it really relates the Riemann tensor at slightly different points. Okay, whereas the first one is a constraint. Okay, it tells you that at a single point there are not that many independent parameters. This provides a number of constraints. So we did this calculation of how many, so given the other symmetries of the Riemann tensor, okay, I won't recap all of them right now. Given all these other symmetries, how many independent components are there, and how many do you need to describe the curvature at a single point on a manifold? Okay, and what we found is that there are, at the end of this calculation, we found that there are, in n dimensions, on an n-dimensional manifold, there are n square into n square minus 1 by 12. Okay, these are the number of independent components of the Riemann curvature tensor at every single point on the manifold. Okay, which means, unlike, let's say, the sphere, right, in a two-dimensional sphere, if I needed to specify the curvature at one point, one thing that I could have done, right, and we saw this notion of extrinsic curvature, where I could have defined this as 1 over r square, where r is the radius of the sphere. I could have defined that as the curvature. That was just one number which was sufficient to specify the curvature on a two-dimensional object. Okay. In general, in n dimensions, you need to specify more numbers to specify the curvature. Okay. It's not sufficient just to specify one number. For n is equal to 2, it turns out that f of n is 1. So even this intrinsic notion of curvature will actually agree with that extrinsic notion of curvature. Here I've only shown that the number of components is the same. Number of numbers that you need to specify the curvature is the same. But indeed will show that it can be related to that extrinsic curvature 1 by r square. Okay, and in particular, you can take one component of the Riemann tensor, say, let's say r12, 1, 2. Okay, and all other components can either be related to this either through symmetry, Bianchi identity, so or they are just identically zero. They vanish by some anti-symmetry of the Riemann tensor. Okay, so r12, 1, 2 is, if you specify this, all the other components of the Riemann tensor are known. Okay. So only one number characterizes the curvature at each point in two dimensions. But if you go to higher dimensions, for example, n is equal to 4, which is one thing we'll be interested in, let's say 3 spatial plus 1 time dimension. Okay, it doesn't really matter whether you have a Riemannian or pseudo-Riemannian metric. The number of independent components of the Riemann tensor is always the same. Okay, it only depends on the number of dimensions. So in 4 dimensions, we saw that there are 20 independent components. You plug in n is equal to 4 into this formula, you'll get 20. Okay, so you actually need to specify 20 different numbers in general at a particular point on a manifold, 4D manifold, to really know what the curvature is. Okay, so it's much more complicated than a curvature of a two-dimensional object. Okay, however, in cases where there's a lot of symmetry, again, you know, many components of the Riemann tensor in a particular coordinate system will be related to each other. Okay, we'll see these examples later on. Okay, so now let's come to the new stuff that we're going to discuss today. Okay, so the first thing that we're going to do is look at the second Bianchi identity. So the second Bianchi identity involved derivatives. Okay, so it was something like this: derivative of kappa of the Riemann tensor psi lambda mu nu, plus now I take cyclic permutations of kappa, mu, and nu. Okay, so I move the mu over here, I move the kappa to the end, and I move the nu over here. Okay, and similarly the last term, okay, I move the nu over here and I move the mu to the end, okay, and move the kappa over here. So this is the second Bianchi identity. Okay. Now what we can do is we can take this Bianchi identity and we can contract. So now this is a tensor. Okay. What is the type of this tensor? Well, derivative, okay, acts on the Riemann tensor. The Riemann tensor is of type 1, 3. Okay. And this derivative, we've seen that if you put just an index here, it becomes like an open slot into which you can insert a vector. Into which you can insert a vector. Okay. And so at the end of this calculation, when I calculate the derivative, okay, or this affine connection of the Riemann tensor, then what you get is a tensor of type what? What type of tensor is this? Specify the R and S values. How many vector indices? How many dual vector indices? 1,4. Okay. It has now one upper index and 4 lower indices. Okay. The other important point is because you're using the affine connection, it transforms like a derivative. Okay. So that's another important point to keep in mind. All right. So now that we have this, okay. So this is of type 1,4, and what we're saying is that this entire thing, when I add all of it together, is a type 1,4 tensor. That type 1,4 tensor is 0. Okay, that's what we're saying. Now, a type 1,4 tensor, we've seen that there's this operation of contraction of indices. Okay, so you can use that to reduce the indices. So one vector-like index eats one dual vector-like index, and so it becomes a 0,3 type tensor. Okay, upon contraction. In index notation, it's quite simple to see what this operation of contraction is. We just take the upper index psi to be equal to one of these lower indices. Okay. In this particular case, we'll choose the index mu, okay, with which to contract it. Okay, it doesn't matter which one you choose because except for lambda, if any other one, it's a cyclic permutation. Okay, so let's say we choose psi and mu. So what is that going to give us? Okay, so if you contract psi with mu, okay, let's say in the first term. Okay. Now let's understand what that means. Okay. So the first thing is that this derivative, it commutes with the operation of contraction. Okay. So when I contract, let's say if I have a v mu omega nu, and if I contract them to take a dot product, okay, if I make it this, okay, then this is the same as first taking the derivative of w mu, of v mu, and then taking the dot product with this dual vector w mu, and then then acting instead on w mu, okay, and then taking the dot product with v mu. Okay, so this derivative operation commutes with contractions. Okay, this is something that we showed earlier. Okay, or that's a definition that we gave rather to this affine connection. Okay, so now if this is true, okay, what this means for the first term is that if we had taken the derivative, okay, so under a contraction, what we have is derivative of kappa, Riemann tensor, okay, and then after we take the derivative, this is a tensor of type 1,4, okay, which has these indices, lambda mu, okay. Now this must be the same as if we had first contracted the indices, that is, if we had first contracted the psi and mu indices, and then taken the derivative. So if I first, okay, so the operation of contraction, okay, so we're doing contraction after taking the derivative in this case. But if I had first taken the contraction, then we are taking the Riemann tensor and contracting this upper index, okay, with this lower index. What does that give me? The Ritchie tensor, okay, which is a type 0,2 tensor. Okay, so it's first we contract the indices, so that gives us a Ritchie tensor. And then what are the indices of the tensor? Well, it's some indices. When I add to the derivative, the indices that are left it's going to be a type 0,2 tensor. Okay, and well, it's going to be type 0,3 because I've left this as an open slot. Okay, so now this is a type 0,3 tensor. So the first term is just this. Okay, it's del kappa of the Ritchie tensor lambda nu. Okay, because lambda nu are the free indices over here. Okay, but that's not true for all the terms. Okay, so now if we look at the second term, I'm still contracting the psi and the mu index. Okay, this xi and the mu index. So that is not going to give me any kind of Ritchie tensor, right? That's still taking a derivative with respect to the Riemann tensor, And then I'm using, I'm summing, I mean, taking the dot product. So at the end, I get a type 1,4 tensor, and I'm contracting this index with this index. Okay, so that nothing changes in this term. And then the last term, okay, involves this, and here again, I'm taking xi with mu. Okay, now here what I can do is I can think of it as, again, let me imagine taking the dot product before, or sorry, the contraction before I take the derivative. Okay, so it's del nu, and then first let me take the contraction, okay, of this with this, and then I'll take the derivative. But what is this? What is this quantity when I take this contraction? Sorry? Is it exactly the Ricci tensor? Sorry? A little louder. It's a negative of the Ricci tensor because the Riemann tensor is antisymmetric in the last two indices. So if I exchange these two indices, this is minus r mu lambda kappa, lambda mu kappa, which is minus of the Ricci tensor lambda kappa. Okay, so now basically this operation here is like taking the derivative of the Ricci tensor. I take the derivative of the Ricci tensor, and then the free indices, ignoring this new index, are lambda kappa with a minus sign. Okay, so that's what I get here. Okay, so the third term is, I make a mistake. Yeah, I think I made a mistake. Okay, it's there's a minus sign here. Okay, so these are these three terms now. Okay, now we'll go one step further. Okay, which is we'll now contract further. Okay, we'll contract the lambda and nu indices. Okay, now we can't just contract the lambda and nu indices. Both of them are dual vector indices. So what do we have to do? How would we contract two dual vector indices? Raise it with? Right. So you have to use the metric inverse. So we take g lambda nu. Okay. So, or the other way to think of it is g rho nu. Okay, when we multiply this now gives us, this is the metric inverse, and what we do is we sum over nu. Okay, so this is like taking a dot product of a 0,2 tensor with, what is this? This is a 0,3 tensor. Sorry, a 2,0 tensor. Okay, because a 2,0 tensor, this is a 2,0 tensor. The inverse metric is a 2,0 tensor. Then I dot it with a 0,3 tensor, and the dot product of that means that I'm taking one index of this and making it eat one index of this. So the net result of that is going to be a 1, 2 tensor, okay, with this raised index. And now I make this this upper vector eat one lower vector. Okay, so basically I'm contracting the row with something else. So in this particular case, I'm contracting the row with lambda. Okay, so that gives me this. And so at the end, what I'm going to be left with is a type 0,1 tensor, which only has a free index kappa. Okay, so that free index kappa is what's left over. So let's work out what we get at the end of it. So now g lambda nu, okay, let me combine it with the first term. Now we know that because the connection is an affine metric connection, that means del kappa g lambda nu is 0. Okay, which means we can pull this g lambda nu inside, okay, this derivative. And what it does now is, again, you can think of this contraction of g lambda nu and the Ricci tensor as occurring before you take the derivative. Okay, so if it occurs before we take the derivative, then it's really just acting on the Ricci scalar. Okay, so now it's just a simple derivative on a Ricci scalar because I take the Ricci tensor g lambda nu before I act the derivative. Okay, so this is just the Ricci scalar, and now this derivative acts on that Ricci scalar. Okay, so this is the first term. The second term now, okay, is a little more complicated. Okay, so let's look at it. Okay, the second term is minus del mu, and now again I'll contract this g lambda nu with r, okay, before I take the derivative. Okay, so when we do that, before we take the derivative, we have g lambda nu r mu lambda nu cap, sorry, there's a plus sign. What is this equal to? Okay, the thing, let's just worry about the thing that we're taking the derivative of. What is that object? Negative of? Yeah, let's be a little careful with this, okay? So we can temporarily lower this mu index and we can always raise it later. Okay, so temporarily let's lower it. If you like, you can think of it as I've performed this operation. Okay, so I've lowered this index and I've pulled out a g mu prime. Okay, and then I have nu lambda nu kappa. Okay, and I have a g lambda nu here. Now what I can do is I can look at this and I can think of this as r mu prime. Okay, and I can exchange these two indices. And when I exchange those two indices, I get a lambda mu prime. Okay, and when I and now I have nu kappa. Okay, and this g lambda nu raises this lambda index and makes it a new index. Okay, so this is now r nu mu prime nu kappa, but there's a minus sign. Okay, the minus sign is because I exchange these two indices, and the Riemann tensor is negative, is antisymmetric when I exchange those two indices. Okay, is this step clear? Are you guys following along, or any questions about this? Okay, I mean, these kind of manipulations need to be very, very clear because you'll have to use them very often. Okay, especially when computing the components of a Riemann tensor. Okay, any questions online or in class? You can ask right now. Okay, and then now we can look at this as this is the Ritchie tensor, okay, mu prime kappa raised through this g, okay, to some mu prime mu. Okay, it doesn't matter whether you write this as mu prime mu or mu prime, right? Because g is symmetric. All right. So this is the thing that we're taking the derivative of. Okay, this is the thing that we're taking the derivative of. Or equivalently, I can regard this as taking the derivative of the Ritchie tensor, where I raise the mu prime index, okay, to make it a mu kappa type index. Okay. So this is the thing that I'm differentiating now, and when I differentiate, I contract the indices of the thing I'm differentiating with this index of the Ritchie tensor. Okay. So what I'm going to get is this term. Okay, the second term is minus del mu of Ritchie tensor, and now I've acted with the derivative and the indices of whatever I get after action. It's some nu and kappa, and this nu I set equal to mu because I'm contracting this with this mu over here. Okay, so this is what we get at the end for this term. Okay, and now for the last term, okay, we are contracting the indices lambda and nu. Okay, so once again, it's like we're raising this lambda index and making it a new index. Okay, after that contraction, but then this is a dummy index which I can just label by mu. Okay, so this third term is exactly the same as what we get from the second term also after contraction. Okay, so now the first term is del kappa r. The second term is minus 2 del mu, this is the second and third term combined, is minus 2 del mu of the Ritchie tensor. Whatever I get at the end of it, I want the mu kappa component of it. Okay, this is what at the end of taking the derivative. Okay, this is equal to 0. All right, and you can see that there's only one free index, which is kappa. Okay, so this entire equation is saying that there's a particular 0, 1 tensor. Okay, if I evaluate that 0, 1 tensor, that tensor is 0. Okay, this is what this equation is saying. Okay, every component of that 0, 1 tensor is 0, so the tensor itself is 0. Okay, and this is a basis independent statement. Okay, and now finally this entire equation you can recast in a slightly simple way. Okay, you can recast it as saying let me change this kappa index to a mu index. Okay, and let me write this as a delta. Okay, so r times delta. Okay, where delta is the thing I'm differentiating. Okay, you can think of it as, let's say there is delta is 1. Okay, if mu and kappa are identical, it's 0 if mu and kappa are not identical. However, when we take the derivative of this, okay, as we've discussed before, you put the indices outside, in the sense that first you differentiate. Differentiation in general you can think of as, I mean, if you like, you can just pull this delta outside, okay, it doesn't really matter, okay, because this del mu will just act on a scalar, so it's just acting on R, okay. But what I can do is I can symbolically write it as, let me first differentiate R delta, and then let me pull the indices on this after I differentiate, okay. And the second thing that I'm differentiating is a tensor, okay. So this is the Ritchie tensor, and after I differentiate the Ritchie tensor, I put the indices mu kappa on whatever I get, okay. Now what you do is you define, okay, so what you see is, oops. Sorry, maybe there's a slightly better way to write this. Okay, I can raise this kappa index, okay, by multiplying by metric. Okay, so I can multiply by metric, and I can raise this kappa index. So if I raise this kappa index, what I have is del mu R, and effectively what I have now inside, I can pull this inside, okay, and then this is just R times G. Okay, so this is 0 to tensor. Okay, this is a Ritchie scalar multiplied by 0 to tensor minus twice of the Ritchie tensor, which is also a 0 to tensor. Okay, I differentiate this 0 to tensor, and at the end, what I it's an upper 2 0 index. Okay, so it's an upper 2 0, and this Ritchie tensor also, since I've raised the index, but I pull this G inside, and this is Ritchie with upper indices. Okay, and this is also a type 2 0 tensor. Okay, and this is so whatever I get at the end of it times, I take the mu nu index, okay, of that, and that is equal to 0. Okay, so now what we're saying is that there is a particular tensor. Okay, there's a tensor field which is defined on the entire manifold, and if I differentiate that, if I take the affine derivative of that, okay, that derivative of that is 0. Okay, so this is a 2 0 tensor. I differentiate it. When I differentiate it, I get a tensor of type 2 1. Okay, that tensor of type 2 1 is 0. Okay, that's what the statement is. What is this tensor that we're differentiating? That tensor that we're differentiating can be written like this. Okay, so I'll call this entire thing capital G. Okay, so in components, capital G mu nu is, well, it's Ritchie tensor mu nu, okay, minus half G mu nu R. Okay, so this thing here is minus twice of G mu nu. Yeah. Sorry? Yeah. So you can think of it as I contracted the delta indices with the G index. And so what this becomes is G kappa mu inside. Okay. See, the reason why it's confusing to write it in this way is because, strictly speaking, derivative acting on a scalar, right, doesn't have any extra indices after that, right? It just, as we've seen before, so if I take derivative along x of a scalar, this is just x acting on that scalar, right? So there's no extra index floating around. That delta is kind of an artificial thing that we put in, okay? And if you like, one way to think about delta, okay, or delta mu nu, one way to think about delta mu nu is to think about it as an inner product of two metric tensors. G kappa. Okay. And now I can think about the inner product, differentiating the inner product of two metric tensors. Okay. So it can first act on one and then act on the other. Okay. Okay, so at the end, what we've shown is there's a particular tensor. Okay, this tensor is called the Einstein tensor. Okay, and it's actually very important for a general relativity. Okay, but basically all this just followed from the second Bianchi identity. We haven't done anything else. We just took the Bianchi identity, did a set of contractions. At the end of these contractions, what we showed is that the derivative, this affine derivative of this Einstein tensor is 0. Okay, so this Einstein tensor is, let's say, a type 2 0 tensor. Okay, we can always raise and lower the indices, it doesn't matter. Okay, and you can always raise and lower the indices inside the derivative, it doesn't matter, because the derivative acts trivially in the metric. Okay, it doesn't differentiate the metric, right? Because that's what we mean by an affine connection which is compatible with the metric. Okay, so now when we differentiate the metric, when we differentiate this g mu nu, so we're saying that this del mu g mu nu is 0. Okay, and this g mu nu defines some Einstein tensor. Okay, this is just some identity that we've proved about some particular combination of the Ritchie tensor and the Ritchie scalar. Okay, at the moment this doesn't seem to be particularly significant. What we'll see later is that this is actually significant when you try to write down the equations of general relativity. Okay. Okay. Any questions here? Scroll up. I want to raise the kappa index. Yes. That would be absorbed into the kappa we raised. Yeah, that's why I have a G here and a free index nu here. Yeah, sorry. Okay, let me just do it in a way that makes this transparent. Okay. So let's first pull this G inside. Okay, and let's write this delta as G mu sigma G sigma kappa. Okay, that's what I mean by delta sigma kappa, delta mu kappa, right? By definition. So when we pull this inside, we now have R times G mu sigma G sigma kappa G kappa nu. Okay, and this is the thing that we're differentiating. Okay, the thing that we're differentiating now, let's contract all these indices. That is just going to be equal to, when I contract this, I get G mu sigma G sigma nu. When I contract, is now delta sigma nu, and this now sets sigma equal to nu, so this gives me G mu nu. Okay, delta function, this is a Kronecker delta, so whenever sigma and nu are the same, right, it sets, it basically sets sigma to be identical to nu when I sum over sigma. Right, so at the end what I just get is R times G mu nu. Okay, and that is the thing that I'm differentiating, which is a type 2-0 tensor. And so I first differentiate, then I put the indices. Okay, and we understand what that means, right? For if we differentiate any tensor of type this, okay, so what we do is in components, this is partial kappa T mu nu plus gamma kappa mu sigma T sigma nu. So this, every vector index has to be treated like this. Gamma mu using the connection, the metric connection over here. Okay, and then we have sigma, sorry, the kappa sigma, and then we have kappa del gamma nu kappa sigma T mu sigma. Okay, so we're doing this differentiation. This is what we mean by first we differentiate, then we put the indices. Okay, because not every term here has the same indices mu nu on the tensor. Okay, the components of the tensor get mixed under this differentiation. Okay, because of the parallel transport. When you parallelly transport the tensor, it picks up additional components of the tensor get added. Okay, to a particular component. And then we're contracting. Okay, so what this means is now if we set this equal to mu, so everywhere on the right hand side you set this equal to mu. Okay, so this is what we mean by this symbol. Okay, any other questions? Anyone online with questions?
Sir, in this case, like in the last term, Why isn't it T sigma mu? Because we don't know, like if T is symmetric, then it is fine. But if T is not, then like how to put in the indices? This.
Here?
Yes, sir. Yes, sir.
No, so what you do is each index of T, you replace it by this dummy index sigma. Okay, that's the rule for the affine connection. I mean affine derivative. So first we replace the first index and we put this dummy index sigma, and we put this index sigma over here. Then we replace the second index by sigma, and we don't change the first index, and this new index gets pulled out over here. So this is a general rule which is valid for any tensor of any rank. Right, we're replacing one index at a time. We're not changing the position of the index which we're replacing. So you can't in general say that T mu sigma is equal to T sigma mu. This may not be true. Unless it's a symmetric tensor. Does that answer your question?
Yes, sir. Yes.
Can you guys hear him? No, it's too faint. He was just asking if, I mean, how are you sure about the ordering of these indices? You have to be careful about the ordering of these indices. We don't have to be careful because we're making the specific choice of a symmetric Christoffel connection. We don't really have to be too careful about this lower index, okay, over here, because it's symmetric, okay. But strictly speaking, you can be careful about those lower indices also. There's a particular definition with where, let's say, only the second index is the repeated index sigma, and the first index is not. Oh, sorry. Yeah. Okay. Actually, I forget. I'm being careless here because I know that I'm using a symmetric connection. Okay. But you have to be careful on the indices on a tensor. If the tensor is not symmetric, you can't just exchange the indices arbitrarily. Okay. G mu nu. With one upper, one lower. So am I contracting the indices of this delta? This one. This is a scalar. This is a tensor. This will be, sorry, yeah, okay, if you like, this is actually a 1-1 tensor. Okay, and I'm contracting these indices. So first I take the tensor product. Okay, so let me think about these indices being different. Okay, then when I multiply these out, what I get is a 3-1 type tensor. When I contract the indices, I make this kappa the same as nu. So the result is a 2-0 tensor. What I mean by Ritchie is the raised Ritchie tensor. Ritchie with the raised indices. Okay, so of course I have this. This is how I defined it. But you can also raise the indices of the Ritchie tensor with the metric. Okay, and that I'm also denoting as Ritchie. Okay, even though you have to be very careful that these are different things, because one has, in general, the metric components are not just ones, right? So the components of the upper Ritchie tensor and the lower Ritchie tensor, these are not the same. Right, the mu nuth component of this is not the same as this, right? Well, okay, that I know it's a bit confusing, but this is the notation that's used in all the books, right? So I can do this, right? I can write this as, let's say, I could denote this as Ritchie upper, but for the metric as well, you should really use a different symbol, right? Because it's sort of like a metric inverse, okay, mu nu. Right, it's not the same components as G. So this is a bit of an abuse of notation. Okay, so the abuse of notation is this: we use the same symbol T for a tensor of type nu1 through nu_n. Okay, the abuse of notation is this: if we have a type nm tensor, okay, we can change it to a tensor of arbitrary type PR, where P plus R is equal to n plus m, by raising and lowering an arbitrary number of indices. Okay, so I can always raise any number of these dual vector indices, lower any number of these vector indices. Okay, and that would give me another tensor of some different type, where the total vector plus dual vector indices is fixed. those are actually different tensors, right? Those are different tensors, but we'll denote them with the same symbol t. Okay, we'll just lower and raise the indices, okay, like this to tell us what we have done. Okay, so strictly speaking, this is not the same tensor as this. Okay, because here I've raised and lowered an index using the metric tensor. Okay, the abuse of notation is to use the same symbol t for both those objects. Okay, it's just to avoid going on introducing letters for everything that we do. Okay. But you should be very, very careful when computing quantities, because something with a raised index, something with a lower index, these can be very different if their metric is not simple, right? Okay, there's one more mathematical thing to do, okay, before we move to trying to connect these mathematical ideas to general relativity. Okay, so what we'll do is let me just go back to that lecture on curvature. Yeah, so I told you that there are a couple of different notions of curvature, okay, which are all equivalent. So the first connection was that initially parallel vectors remain parallel under parallel transport, okay, or parallel transport of a vector around a closed loop keeps the vector unchanged. This is in flat space, okay, or initially parallel geodesics remain parallel to each other at all times, that is parallel lines remain parallel. Or the intuitive thing is ants walking along initially parallel straight lines never bump into each other, neither getting closer together nor further apart. Okay, really, if you have to think about curvature, right, especially if you're trying to think about curvature even in 3 dimensions or 3+1 dimensions, right, the intrinsic notion of curvature is what you should think about, right? You have no way of getting outside of the 3 spatial dimensions that you live in, right? Versus if you're on the surface of the earth, you can imagine that getting off of it and viewing the entire earth and visualizing that curvature, right? But there's no way to do that in 3 dimensions, okay? So if you really want to understand how you'd visualize curvature in 3 dimensions, you have to first imagine how you'd perceive curvature in 2 dimensions if you could never get off of that 2-dimensional surface, right? If you could never get off the 2-dimensional surface, then the idea of one notion of curvature is imagine that you and a friend are walking in what you think are parallel lines, but you end up bumping into each other. Okay? So if we just walked along the surface of the earth and always tried to stay parallel to our initial trajectory, we would and starting at the equator, heading upwards, okay, we'd eventually collide at the North Pole. Okay, so so this is really basically the intuitive idea, okay, that which is saying the same thing here. Initially parallel geodesics. So if you take geodesics on the surface of the Earth, okay, initially near the equator they are parallel, but like as you get to the North Pole, they come closer together. Okay, so geodesics can either come closer or move away from each other. That is, they don't always remain parallel to each other. Okay, so so basically what we'd like to do is we've defined curvature using this notation, this notion. That is, if I parallelly transport a vector around a closed loop, it won't come back to itself. Okay. Uh, Equivalently, we looked at transport along 2 different loops, 2 different paths, and we compared the vector here. Okay, these are equivalent things, right? Because I can just imagine that I continue the path on this way, right? Um, and instead of stopping here, I compare the vector after a full comparing after taking it around a full loop. Okay, we would still get this notion of the Riemann curvature tensor. What we'd like to do is we'd like to see the equivalence between these 2 definitions of curvature. That is, parallel transport of a vector around a closed loop keeps the vector unchanged. Okay, can I also see that in terms of geodesics? Okay, can I see that a curved space, in a curved space, we've seen that parallel transport of a vector around a closed loop does not keep the vector unchanged. Is it also true, or can I show that in a curved space, that same notion of Riemann curvature also shows me that initially parallel geodesics do not remain parallel to each other, okay, at all times. Okay, so even if they start out parallel, they may not remain parallel. Okay, or that is, they get closer to each other or further apart from each other. Can we see that? Okay, so that's what we're going to do next. Okay, is something called the geodesic deviation equation, which is we'll try to understand how close or far geodesics are from each other and how that changes as you go along the geodesic. Okay, So let's consider a manifold, okay, and this manifold has a connection, okay. Either in coordinates you can assign a gamma, okay, or if I don't want to talk about a particular coordinate basis, I can think about this affine connection through the derivative operator delta, okay. And let's take a one parameter family of geodesics on this manifold. So what do we mean by that? Okay, so here is one geodesic, here's another geodesic, here's another geodesic, here's another geodesic, okay. We are saying that each geodesic, okay, at each geodesic, so let's say this geodesic, I'm at some point along this geodesic. That point along that geodesic is given by some parameter t, okay. But I also have a way of specifying which of these geodesics I'm talking about, and those geodesics are specified by another parameter s, okay. So if s is equal to some 0, maybe I'm on this geodesic. If s is equal to 0.5, I'm on this geodesic. If s is equal to 0.6, I'm on this geodesic, and so on. Okay, and you imagine that s varies continuously. So as I vary s, I'm continuously getting nearby geodesics, okay, to my original geodesic. So this defines a family of geodesics, okay, which I'll denote as gamma st. Okay, so t is the parameter along the geodesic, and s is the parameter that takes me from one geodesic to another geodesic. Okay, and on a particular geodesic, I have a tangent vector, which I denote as t. Okay, so this is the tangent vector on the s geodesic. Okay, the geodesic which has label s, and and this is the tangent vector at a time t. Okay, time in the sense of geodesic parameter. Okay, so at a geodesic parameter t, I'm at this point on the geodesic. Okay, if at an earlier t, I would be here. At a later t, I'm over here. Okay, and this is the tangent vector at that particular t and that for that s. Okay, so again, s is my sort of my coordinate going along the geodesics. T is my going, switching from one geodesic to the next, and t is my parameter following a geodesic. Okay, as I follow the geodesic, I vary my parameter t. So that's just what I've written here. The parameter s specifies which geodesic we're on, and the parameter t specifies where we are along a given geodesic. Okay. Now we're making some assumptions about this family of geodesics, okay, which is that the map from TS. So we'll assume TS is some, let's say, open interval, okay. So let's say T takes values, let's say between 0 and 1, S takes values between 0 and 1. Okay, so you can imagine that this is some open interval in R2. Okay, so we'll assume that this map to geodesics is a smooth one-to-one map and has a smooth inverse. Okay. Can you tell me how we would quantify this? What do we mean by a smooth map to geodesics? Sorry? No two can intersect. That's one-to-one. Okay, that's the one-to-one relationship.
The map is
what do we mean by
differentiable.
smooth? How do you quantify smoothness?
The map is differentiable, and
the map is differentiable. Good. But what do we mean by differentiable? Gamma st gives me points on the manifold or points on a geodesic. So what do we mean by differentiable?
So we can continuously jump from this coordinate.
Sorry. Let him just finish. I mean, I can't hear what he's saying. Can you say that again?
I mean, we can continuously switch from this parameter, this system of coordinate
to?
I mean, to real parameter to the family of geodesics.
So see the family. So TS is a mapping from this interval TS to points on the geodesic. What do we mean by this being a smooth mapping? These are points. So you said differentiability, but I can't differentiate functions to points. What can you differentiate? Rahmat. Sorry? I agree it's a function of S and T, but the function of S and T is mapping you to points on a geodesic. Yeah. Right, that's the important point. You have to map the points to coordinates now, right? You have to assign coordinates. So only when you assign coordinates, then there's a notion of smoothness. Okay, since it's a manifold, you can always assign coordinates. All right, so this is mapped to some coordinates, and these coordinates are in some Rn, where the manifold is in Rn. Okay, and then what we're saying is that this map, okay, so this is through some phi, okay, which gives you coordinates. Okay, and we're saying that this composite map, which is gamma st phi circle gamma st, this is differentiable. Okay. Okay, Pravesh, do you get the idea? Okay, this is the extra step.
Yes, sir.
Okay, you have to map it to a coordinate chart, and only then the notion of differentiability makes sense.
Yes.
Okay, so once you do that, then it's if this map is C infinity, okay, then we say that this is smooth one-to-one and it has a smooth inverse. Okay, so sorry, we're assuming it has a smooth inverse. That is this. So anyway, the coordinate chart has an inverse by definition. Okay, we are assuming that this map also has an inverse. Okay, which is smooth. Okay, so now we can think of this as basically these geodesics, okay, are spanning a two-dimensional submanifold of the original manifold M. Okay, so whatever my original manifold, these geodesics, this family of geodesics is mapping out a 2D submanifold. Okay, because it's a one-parameter family of geodesics. Okay. So we'll denote that 2D submanifold as sigma, okay, and sigma has coordinates. We can think of this reverse map as basically just assigning coordinates to the points P. Okay, this reverse map is assigning coordinates to the point P, but of course it's only assigning them 2D coordinates, which is sufficient as long as you're talking about points on this geodesics, on these geodesics, right? So on that submanifold, we've essentially assigned it a coordinate chart, okay, where we've given it coordinates S, T. Okay. So again, as long as the geodesics are not intersecting, okay, this is perfectly fine. Okay, as long as the geodesics don't intersect, this is perfectly fine, because then your map is one-to-one, okay, by assumption. Okay, now what you can do is see, now that you have a submanifold which is two-dimensional, what you can do on this 2D submanifold is you can define tangent vectors on this 2D submanifold. So you can think about T as partial T, okay? That is the tangent vector at some point, okay, this is at a particular S, okay, so I'm fixing which geodesic I'm on, and I fix what T I evaluate this derivative at. That tells me that I'm evaluating, let's say, at this point, okay, so I'm fixing the T coordinate, I'm over here, and this is the tangent vector here. Okay, and similarly, I can also evaluate what is called a deviation vector. Okay, that is, I can evaluate a vector partial S. Okay, which is called a deviation vector. So at the same point, I can now think about the vector like this. Okay, which is X. It's a deviation vector. Okay, it's basically a vector sort of in the direction of changing the parameter S. Okay, that's what we mean by this deviation vector. Okay, so T are tangent vectors to the geodesics, and X are what we call deviation vectors. Okay, they parameterize a direction which is away from the geodesic. Okay. Now, if we assume that the geodesics are finely parameterized, okay, then they satisfy this rule. Okay, that is, the tangent vectors satisfy derivative of along T of T is equal to 0. Okay, now this derivative you can think of as either the derivative on the full manifold, or you can think of it as the derivative on just this 2D manifold. Okay, where I've sort of inherited this operation of derivative. Okay, I've just projected that derivative map onto this 2 dimensions. Okay, at least derivative on T is well defined. Okay, with this projection. Okay, what we won't think about this. We'll just really think about. This is some 2D submanifold embedded inside, some m-dimensional manifold, n-dimensional manifold. Okay. Yeah, and we can think about these T and X. These are also sort of vectors, right, inside the n-dimensional vector. Sorry, if I take this point P inside the original manifold M, okay, these t and x are also tangent vectors of the point P in the full manifold M. Okay, there are other tangent vectors. Those other tangent vectors are, in sort of different directions, which do not span this geodesic space, this 2D subspace. Right? Those tangent vectors point in some other directions. But these are, out of all the tangent vectors, okay, this is an n-dimensional space, n-dimensional vector space. Okay, out of that you've picked out a 2-dimensional vector space which spans the vector space at the point P. Okay, maybe I'll skip this part and yeah. So now let's come over here. Okay, so now what we can do is, so let's suppose we have these geodesics. Okay, and roughly speaking, at this point, t is the tangent vector, x is some displacement vector. Okay, x is a displacement vector to a nearby geodesic. Now what we can do is, and now at this point, t is a tangent vector and x is another displacement vector. Okay. Now what we can do is we can ask under parallel transport, okay, of this x, of this displacement vector. So we know that del t of t is 0, okay, but we want to know if this is 0 or some non-zero quantity. That is, if I transport the deviation vector from here to here, does it remain unchanged? Okay, does the deviation vector remain unchanged? Okay, so this in some sense is defining some kind of velocity. Okay, this is a velocity which is sort of a measure of what is the velocity of this geodesic relative to this geodesic along the deviation direction. Okay, so as I change, as I go along the along the tangent vector, okay, does this x vector, as I go from here to here, so if I compare this x with x prime after a parallel transport, has it changed? Okay, or is it the same? Okay, if it has changed, then we say that there is some velocity. If it has not changed, we say that there is no velocity. Okay, so we define this quantity v, okay, and this v gives the rate of change along a geodesic of this displacement vector x to an infinitesimally nearby geodesic. Okay. Okay. Now, so this v can be interpreted as a relative velocity. Okay, but what I can now do is I can define a relative acceleration. Okay, I can define a relative acceleration. So what I can do is this v itself is a vector. Okay, this v defines a vector field. So this del t of x is evaluated at some point p. Okay, and this is a vector. Okay, and this v therefore is also a vector. Okay, at the point p. Okay, so now I can ask. So there is some vector associated with the point p, which parameterizes basically the change in x. Okay, under parallel transport. Okay, so roughly the way to visualize this is, here are two geodesics. Okay, imagine these geodesics are sort of getting closer to each other. Okay, and this is x, let's say in one case, and this is the vector x in the next case. Okay, after parallel this is the vector x at the point p prime. Okay, so now what we've done is, by this derivative along t, okay, of the vector field x, we've sort of compared the vectors x prime and x parallelly transported to the point p prime. Okay, and that we said is the velocity v. Okay, and so the difference between those two is roughly speaking this velocity v. Okay, it's sort of an infinitesimal version of that. Okay, It's a difference between x prime minus x parallelly transported divided by epsilon, which is the amount you parallelly transported, okay, the amount of displacement. So now this defines some vector v, okay, which is the deviation. It's sort of this is the vector v. It's a difference between x prime and x parallel, okay. And now what we do is we ask what is the rate of change of v itself, okay, as we move along the geodesic. Okay, so that is, as I move from here to here, there's another vector v prime, and I want the difference between this v prime and this v, okay, after parallel transport. So we take a second derivative along the direction of the geodesic. So this is something like an acceleration, okay. So this is like an acceleration of the displacement vector. Sorry, it's derivative of v, and v itself is the derivative of x, okay. So this is an acceleration of the displacement vector, okay. So this is some measure of whether these nearby geodesics are accelerating towards each other or not, okay. It's giving you some measure of that. Okay, now it can now this acceleration, let's compute this acceleration, okay. So let's compute this acceleration, del t x, yeah. No, actually the velocity does not, okay. It's actually always possible to, I think it's always possible at any point on the curve to reparameterize it so that the velocity is 0. Okay, I think that's the part I skipped over. Okay, let me just check if that statement is true. Yeah, so basically what you're arguing is if the velocity is non-zero, these displacement vectors are changing, and therefore the geodesics are either coming closer or moving further apart. No, that's not, at a point you can do this, but you can't do it at several points simultaneously, right? Okay, I'm not sure if that statement that I just said is true, that the velocity can always be parameterized at a point to be 0. So you have some freedom in the choice of x, okay? Because what do we mean by this deviation vector? Okay, so let me just give you the intuitive idea of this freedom in x, okay? So this deviation vector, we sort of imagined it as orthogonal in some sense to t, okay? First of all, to be orthogonal, you need to have a metric, okay, to talk about orthogonality. But assuming that you can have a assuming that your space has a metric, then yes, you can choose x to be orthogonal to t. It is possible to find a parameterization of these geodesics S such that Tx is 0. Okay, this inner product is 0. But you could have chosen other parameterizations. Okay, if you choose another parameterization, roughly speaking, if you parameterize each geodesic differently, you have an affine parameterization of the geodesic. So this geodesic is, let's say, parameterized by t. This geodesic is parameterized by t. This is at location S1. This is at location S2. Now, what we've seen is that there is a freedom in your affine parameterization itself. That is, if I choose another parameter along this geodesic, let me call it t prime, which is at plus b. Okay, this is called an affine reparameterization. Okay, if you do this kind of affine reparameterization, your geodesic equation is unchanged. Okay, so it just so now if you do this affine reparameterization, t of course will change. Okay, But the important thing is now you can do this affine reparameterization differently for S1 and for S2. These two geodesics can have different reparameterizations. Okay, so the first geodesic, or in general, these coefficients A and B can depend on S. Okay, this is the freedom that you have in terms of how you reparameterize your geodesics. So if I reparameterize my geodesics this way, you can show, I'm skipping over this and it's in the notes which I'll upload. Okay, your deviation vector x, okay, gets changed to x plus something times t. Okay, so in other words, if I define my t is equal to 0 to be this point and t is equal to 1 to be this point, intuitively what I've done, if I reparameterize one curve here, then now this point is, let's say, t is equal to 0, and this point is still t is equal to 0 on this geodesic. Okay, so what this does now is it makes the deviation vector sort of like this, okay, rather than this way. So it changes the deviation vector. So instead of the old x was like this, okay, the new x, okay, which is x prime, is the old x plus something along the t direction. Okay, so so this is sort of my reparameterization. What happens to x under reparameterization? Okay, so x can change like this. Now, if x changes like this, del x t, okay, sorry, del t x, this is what we were evaluating. So I have the freedom to change x. In that case, del t x will be del t x plus something times t. But in that case, it would be del t x plus, and this quantity only depends on s, it doesn't depend on t, so I can pull it outside. So I guess the velocity doesn't change under that reparameterization. Okay, so yeah, I suppose under the affine reparameterization, the velocity deviation vector does not change. No, sorry, I have to do something else here. I have to change this t to t prime, but maybe that's a trivial change. Yeah, so I have to change this t as well, okay, to some t. So when I make this change, t also changes, okay. It's just a scale factor, but you see that the scale factor will pop up here, okay. So this t prime will change by some scale factor, which is that scale. So the normalization of that velocity will depend on what that scale factor is, okay. It might end up being the same, depends on how you reparameterize, right? But there is no fixed notion of what that velocity itself means.
Doesn't this actually prove quite sort of in the sense that
Sorry, there's someone asking. Sorry, can you speak up? And I can't see who's speaking.
sir, so doesn't this sort of prove the point that we proved that nabla t of x is the same as 1 by a of s times nabla t of x?
Yeah, so
So then it will have to be 0, something like that. I'm not sure.
No. This is not the same. What I'm saying is, this is the new deviation vector after I reparameterize. Okay, this is what I'm arguing. Okay, so the new deviation vector will be related to the old deviation vector by some scaling. Sorry, not the new velocity will be related to the old velocity by some scaling. Okay, after I reparameterize.
Yes, sir. Got it.
Sorry, go ahead. Del Tx is the velocity. No, this is not the velocity of, let's say, the particle, right? It's a measure of del Tx will be 0 in flat space. Yes. Yeah. No, if you traverse one geodesic faster than the other, that's what we argued, right? That as long as your parameterization is still. Yeah, because this is just a scaling, right? So that this is now del t of t. Which is yeah, maybe the velocity is also a signature of curvature.
This velocity should be proportional to the curvature of space.
Actually, it turns out that the acceleration is proportional to the Riemann curvature. The velocity, I don't know what it is. I mean, I don't know how to relate it to the curvature. I don't know if you could hear that. And basically, he said that this velocity should be related in some way to the curvature. Um, yeah, maybe it is. Maybe from what Sahas, what you said also. But
acceleration is related to the curvature. It means that if you keep the velocity is non-zero, but it stays the same at all, like any parallelly transported.
if the velocity does not change, yeah.
If the velocity does not change as when you parallelly transported, that should still be in that space, right?
That should still be flat space, yeah. Yeah, okay, yeah, sorry, that's right. So if you have a straight line and this is another straight line, they are getting further away from each other, right? Sorry, parallel straight lines. No, that will still have a constant. This will still be constant for these vectors. Yeah, I think that. Okay, so let me just say this. Okay, so this will be 0, no matter how fast you traverse the other one. Okay, this will still be 0. Okay, but I could take a family of geodesics, which imagine instead of taking them like this. Nabla t of x. It will be 0. That's what I'm arguing. That basically, if I use an affine reparameterization, I can always ensure that I'm traveling both of them at the same rate. And we argued that this would be equal to this up to a scale factor. So if one is 0, the other is also 0. Right? But yeah, I think the answer is this. Okay. So this is a geodesic, but this is also geodesic. Okay. And these geodesics. So if I only look at this region, let's say where the geodesics don't intersect. So I have a one parameter family of geodesics, let's say given by an angle by which I rotate this line, okay, in flat space. Now these geodesics are actually getting further away from each other, okay. So the velocity is increasing, okay, but the velocity sort of stays the same, okay. The deviation vector stays the same, okay. The velocity vector stays the same. It's only when the acceleration is non-zero that that the space is curved, okay. So yeah, it's also the choice of which geodesics you use to see this. No, so the
Sir,
argument that we're making is for general geodesics, we can define a velocity vector. It's just a family of geodesics. We're not saying anything about parallel or not parallel to each other. Sorry? Sorry. Can you just repeat that again? No, they can have different velocities, but I can do an affine re-parameterization. Okay, which means one is, let's say, t and the other one is t. Okay, but let's say along, so along one of them, I reparameterize t by some s-dependent factor. Okay, or in general, for each geodesic, I reparameterize it by some s-dependent factor. This is an affine reparameterization, which still ensures that it satisfies the tangent vector satisfy the geodesic equation. If you don't reparameterize, that's it. This would be x here. No, but okay, yeah. Yeah, in flat space, this is all you're doing by that reparameterization, right? You're leaving. Yeah. So the scale factor would be something like this. The separation is constantly increasing. Sorry? Yeah, okay, so this is
all the x's are getting scaled by the same amount.
all the x's are getting scaled. Sorry, are you talking about these points?
Yeah,
with
one
coordinate?
of the x vectors, they're getting scaled by the same amount for every point of the geodesic. So you can't take x from like.
No, so if you wanted to ask about x itself, okay, x, you're asking what happens to the vector x under a reparameterization. Is that what you're talking about?
Oh yeah, yeah.
Because x becomes, the new x is some x plus something times t.
Yeah, that's right.
Um, yeah, I'm not sure about these velocities. Okay, maybe we can go through that proof. Okay, let's discuss the acceleration, then we'll go to the proof of this reparameterization and try to understand the velocities themselves. Okay. Okay. So we can define the acceleration. This, sorry, is there a question online?
Sir, in one figure you have shown the intersecting line. Na?
Yeah, we're assuming that we're working in a region where the geodesics don't intersect.
Okay. But in the figure initial, you have shown the all t has the same direction, na, for all geodesics.
Same direction. Well, I mean, this is just symbolic, right? You can imagine that this is on the surface of the Earth, and these, sorry, if you're looking near the equator, they all look like they're kind of going in the same direction. But at some point, they're going to converge, right?
Okay.
Okay. Okay, so now we'll do a couple of things. Okay, so we'll define this as the relative acceleration, okay, of an infinitesimally nearby geodesic. That is, we take the rate of change of that velocity along the tangent vector, okay, along the geodesic. So this gives me a vector at each point on this submanifold sigma. Okay, and now what we can do is we can evaluate this. Okay, and we'll evaluate it using coordinate-free notation. Okay, if you look in any book, you will typically see this in coordinate-dependent notation. Okay, I want to show you the power of how to do this in a coordinate-free notation. Okay, so in a coordinate-free notation, the first thing that we'll use is the fact that we're using a torsion-free connection. Yeah, go ahead. Can you be a little louder, please? Yeah, sorry. Okay, is that better? Yeah. If there's some way to hide even all the other stuff on the screen, let me know. I haven't figured it out. Okay. focus mode. Where is that? Yeah, I don't know why I can't see it. Okay, anyway. Okay, I'll try after class, just let me know. Okay, so the first thing we'll use is the fact that we have a torsion-free connection. So torsion, as we defined in the last class, torsion of, let's say, xt was defined as del xt minus del tx minus Lie bracket of xt. Okay, but if we chose x and t to be coordinate basis vectors, okay, that is if we chose x to be partial partial s and t to be partial partial t, okay, and you imagine that these are coordinate vector basis vectors in the full manifold. So in your full manifold now, you have the coordinates of a point as st, which are the geodesic coordinates along this geodesic, plus you have some other coordinates x1 through xn minus 2, okay, where it's an n-dimensional manifold. So two of those coordinates you use as these geodesic coordinates for points along these geodesics, and the other coordinates you use as these x1 through xn. Okay, so you imagine that this is a coordinate patch that's valid on these. Okay, so roughly speaking now, this xt, okay, these are coordinate basis vectors where I'm holding here t x1 through xn constant, and here I'm holding s x1 through xn minus 2 constant. So what is this xt going to be? What is the Lie bracket of xt? If you remember what this was, this is x acting on t minus t acting on x. Sorry, not exactly. It's xt minus tx. Okay, where x acts on t and then x acts on anything else to the right of it. Okay, so you could act this on a function, for example. So xt acting on f was x acting on t acting on f minus t acting on x acting on f. What is this going to be?
0.
0. Good. Why?
The partial derivatives will commute. Del x and del t. Del s and del t will commute.
Sorry, if you're online, I just reconnecting my laptop. Just give me a second. Okay, can you hear me?
Yes, sir.
Okay, sorry about that. I got disconnected. Just give me a second. Okay, so yeah, so Toshif, before we got disconnected, you said it absolutely right. The partial derivatives, partial s, partial t commute, right? It's only if I had a non-trivial function here, right, of coordinates that these would not commute with each other. Okay, if these are coordinate basis vectors, they commute with each other. Okay, and then this is zero. So the Lie bracket is zero. So torsion free means that this entire torsion is zero. Okay, the Lie bracket is zero, which means del xt is equal to del tx. Okay, for a torsion free connection. So I can write this del t del xt as I can write this del t del x as del t del x t. Okay, this is using the torsion free condition. Now the next thing I can do is I can subtract from this del x del t t minus del of Lie bracket xt. Okay, and I can add back these terms that I subtracted. So I can add back del x del t t, and I can add back del xt t. Okay, now this is zero because the Lie bracket of xt is zero. Okay, so I'm taking a derivative with respect to a zero vector. That's just zero. Okay, why is derivative with respect to a zero vector zero? Right, because you can think of this as 0 times the basis vector, and I can pull the 0 out here. Right, good. So this is 0, and this is also 0. Why?
Del t is 0 from geodesic.
Yeah, this is a geodesic, so del t is 0. Okay, so both these are 0, but what is this quantity? That's just the Riemann tensor, right? It's the Riemann tensor acting on Tx, and we think of the third argument as T. Okay, or you can think of this as operating on T, as I told you in the earlier class. Okay, so this is just the Riemann tensor acting on of Tx acting on T. So in components, I can just write this out now. Okay, so the muth component of A is R mu nu rho sigma, T nu T rho x sigma. Oh, sorry, I think it's x rho T sigma. No, it's T rho x sigma. Yeah, I think that's right. Okay, this T is here. Okay, this T is here, and this x is here. Okay, so you see that the acceleration, okay, the acceleration between nearby geodesics, it really depends on the Riemann tensor. If the Riemann tensor is zero, the geodesics don't accelerate away from each other. Okay, if the Riemann tensor is zero everywhere in the manifold, there's no curvature. Okay, then geodesics don't accelerate away from each other. If the Riemann tensor is zero, okay, then if the Riemann tensor is non-zero, then the geodesics will accelerate towards each other, either towards each other or away from each other. Okay, so no curvature implies geodesics remain parallel, at least they don't accelerate towards each other. And if the Riemann tensor is non-zero, that is you have curvature, okay, then geodesics will accelerate either towards or away from each other. Okay, uh, okay, so that maybe is a good stopping point. Maybe we can just figure out the thing about the velocities now. Is the velocity zero on a curved space or not? So we're working on this quantity. And roughly speaking, this was x, but I can always reparameterize my curve. Reparameterizing my curve changes this to some t prime and changes this to some x prime. And roughly speaking, x prime is my old x plus something along the t direction. Okay, where this something depends on which geodesic I'm on, so it's s dependent. Um, acceleration. Actually, the thing is, acceleration itself is not non-zero. The thing is, acceleration, if t all these are non-zero, right, then the acceleration is non-zero. At some points, acceleration is.
have the acceleration be 0 over a continuous area, even if you make the velocity 0 at one point on the geodesic, immediately when you move a little bit away from that, the velocity will be non-zero.
Yes.
So you can't make the velocity 0 everywhere on the geodesic in a curved space.
Yes. I think that's right. So what you're saying is that the velocity here, let's say, so this x doesn't change as I go from here to here. Okay, so that is v is 0. Okay.
For a curved space, that v has to go from 0 to non-zero as you move an infinitesimal distance away from that point.
Yeah, so let's just write this out in components. Okay, so del t of x is equal to partial mu mu, sorry, okay. So the velocity is, so v is, sorry, this t is the tangent vector, x is the deviation vector. Now under a definition of parallel transport, this can be 0. Okay, this combination, even if x, the vector x, is sort of changing under a change of coordinates, right? This is coming from how I parallelly transport x itself. So this can be 0.
Yeah, but my point is, it's impossible to make it 0 along the whole geodesic.
It's impossible to make it along the whole geodesic. Yeah.
Sir, I mean, we just proved that the derivative of, the acceleration is basically a derivative of the velocity. So if we can actually make the velocity 0 everywhere, then the acceleration will also be 0 everywhere, and we just showed that that's not.
Sorry, say that again, Anish.
Sir, we just showed that basically the acceleration which we just calculated was essentially grad t of v.
Yeah.
And if at all it is possible to reparameterize it so that v is 0 everywhere, then this would also be 0. Because
Yeah, that's right. If
the,
v was 0 everywhere, or at let's say nearby locations, then the acceleration would be 0. I think that's what Sahas is also saying. Yes. So if there are two nearby locations where v is not changing, it's not. It doesn't even have to be non-zero, right? As long as v is not changing, then there's no curvature. And v is a measure of how much x itself is changing. Okay, I mean, I think the concrete question is this: if v is non-zero but constant, okay, then can you show that there is no curvature at that point?
So then the acceleration is 0, right? Del t x is 0.
Yeah. So clearly from this definition, you expect acceleration is 0, so Riemann tensor is 0, right? But intuitively, if v is non-zero, what is it that makes the space non-curved?
Like intuitively in flat space, if you draw lines that are diverging, as we do earlier.
Yeah, but did we require anything about parallel? These vectors have to be sort of, the tangent vectors can be initially parallel, but they don't have to.
Just take a like patch where they don't intersect and
Yeah, again here. This is one tangent vector.
Yeah. So I think V being zero or non-zero, at least in Euclidean space, tells you if the curves that you are choosing, if the geodesics that you are, the family you are choosing, they are diverging away or they are parallel.
Yeah, okay. So simple thing is in polar coordinates, we choose a family of geodesics to be these radially outward things. Okay. Okay, so something like this, and our coordinates are r theta for each point. Okay, and so theta is basically parameterizing my geodesic, and theta is parameterizing my geodesic, and r is parameterizing where I am along the geodesic. Okay, so r is like t, and theta is like s. Okay, so partial theta takes me from one geodesic to another. Right? It takes me from it's a deviation vector. So partial theta is like x, and partial r is like t. Okay, under some parameterization. Now what we want to know is what is partial px. This is the velocity. This is the deviation vector between two geodesics. Okay, two nearby geodesics. This is, as we've written before. Um, let's use this equation. Okay, maybe we'll have to work it out in components because you need to look at all those Christoffel symbols. But yeah, maybe here you'll see that V is non-zero. Okay, but it's still flat space even though V is non-zero. Sorry?
I would expect V to be non-zero but constant.
V is non-zero but constant. Yeah. Yeah, V is non-zero but maybe constant. So let's see if we can show that. Right? Constant at least along R, it should be R independent. It doesn't have to be theta independent, right? Because what you want is this is zero, but this need not be zero. Okay, so it's basically only this is only a function of theta.
No, I mean, since you chosen all theta, like you chosen a coordinate system, you choose all theta equivalent. I don't see why to change V now. But that's not required. But
Yeah, I would expect it to change with R and not with theta. If you show it doesn't depend on R,
I think it should just be constant. R or theta.
actually it's not true that it won't depend on R, right? What you want is grab this to be grab this to be zero, but that doesn't mean partial, you know, that doesn't mean t acting on v is zero. You get what I mean? I mean, this is not saying.
Grad Tx should be R independent. Right?
No, I don't think that's true, right? What you want is this is zero, right? But this has the parallel transport part in it, right? It has a partial r, but also has a gamma in it, right? Acting on v, right? So this combination is zero, right? So it's not that this v is just going to be r independent. I think v will be theta independent because of the symmetry, but v will not be r independent. Yeah, because the statement is not that it's not changing with r. The statement is that this is going to be zero, right? Because this is basically this, which we argued is zero in flat space, right? This will be zero. But this, if I expand it in coordinates, is something like partial r of v, but then there's also a connection times v, okay? And I don't think this connection coefficients will be zero. Yeah, so you have to work out this gamma r. I mean, I think you'll get this component to be non-zero, right? So if I work out v, V is non-zero in the R direction. Here? Here? And V is V has both a theta and an R component, right? V in general will have a theta and an R component. And we've seen that these components, I think, are non-zero, right? Of the in polar coordinates, gamma, theta, R, theta was okay. So let's leave this as a homework exercise. Okay, we'll try it out before the next class. You just work this out in polar coordinates and see.
Potentially, one thing I can see, I mean, just on intuitive grounds, obviously, I have not done the explicit calculation.
Sorry, say that again. Can you say that a little louder, Anish?
Sir, so we have, I mean, like I'm just trying to sort of intuitively justify it. Obviously, the exact calculations which you're suggesting as homework still are relevant. But essentially, the way I see it, x itself is basically proportional to, I mean, this is a very hand-wavy sort of argument, but x is essentially proportional to the distance. And so, I mean, the velocity itself is sort of constant. Because
okay, it's a little more tricky than that. X is not. X is a displacement vector. It's not really a measure of distance.
sir, essentially x would be something like r times del del theta, right? I mean, some proportionality constant times.
X is just this. Okay. Well, this is one parameterization, I think. You can choose this, I think, in one parameterization. Okay, anyway, I think it's time to stop. So I just wanted to ask for those of you online, was this experience okay, or did it degrade your experience from regular lectures, or you didn't notice any difference?
Sir, I think the only difference was that I could not hear what people were saying offline.
So can you say that louder?
It was sometimes difficult to hear what people were saying offline. Other than you. Otherwise, it's fine.
Yeah, I think they have the same trouble. They can't hear you, and you can't hear them. But yeah, okay. So anyway, for a little while, this is what we'll continue with. Okay. So if it's okay, maybe we'll have all our classes sort of in this format, or maybe we'll do one class a week in this format and one class in the usual online. Okay. Okay. So for those of you online, thanks. I'm ending the session now. Okay. Bye.